Hello, and welcome again to my physics online video lecture series. Today's video, we're going to be talking a little bit about total internal reflection and a little bit about dispersion. So these are two optical effects that are, they're kind of extensions of the law of refraction, and so they usually get talked about in the same chapter as geometric optics, although an argument can be made that these are also wave optics effects, and a very strong argument, I should say. So what are these two effects? Okay, we'll start with total internal reflection. So total internal reflection is basically what happens when you use Snell's law correctly and your calculator gives the result not a number or error or something like that. Basically, total reflection or total internal reflection means you have, let's say, a surface, and maybe this is a low refractive index. We'll call it NL for low and NH for high. So NH is greater than NL. For example, maybe NH is 1.45 per glass, so it's some sort of a glass, and NL is 1.00 like in air. Okay. Now we take a beam of light and we shine it from the low into the high. So here we have our normal line. This right here would be basically like theta H. And we expect for this beam to exit into the low at some other angle. We'll call it theta sub L, such that NH sine theta H is NL sine theta L. All right. But let's, by way of example, consider what would happen if we happen to have these two numbers. And so what if N sub H is, let's say, 1.45, N sub L is 1.00, and let's say that theta from the high end is, say 68 degrees. This is just kind of a randomly picked angle. Okay. So what you want to do is basically get out your calculator or phone or whatever you use to calculate and apply Snell's law. So I've got here my phone. It has a calculator on it. I open up my calculator app. Okay, I make sure that I have sines and cosines, that I'm working in degree mode, that kind of thing. Quick test, I'm going to do the sine of 30, and I'm in radian mode right now, so I need to make sure that I switch over to degree mode. All right, so now let's take sine of 30. Sine of 30 degrees is 0.5. That's as expected. Okay, so that's just me checking my calculator mode. Now let's throw these numbers in. Snell's law says this must be true, and therefore sine of theta L must be N high over N low sine theta high. Okay, so I got 1.45 over 1. That part I don't really need to put in my calculator. Times the sine of 68 degrees. Okay, so sine of 68 degrees is 0.92. I got to multiply that by 1.45. I get 1.34. Okay, so this is roughly basically saying sine theta low should be about 1.34 1.34 something. Now we take the inverse, that's the I and V button on my calculator, inverse sine, so it says sine -1 of 1.34, the number I just calculated, and I hit enter. And you can see I get a domain error. Why is that? Because sine should run from values of -1 up to a maximum of +1. And that means that if I have the sine of some number and I'm getting a number bigger than 1, then I'm outside of that domain, running from -1 to +1. And so there isn't any angle theta that can give me a sine of that angle giving me 1.34. And so physically what happens in this case is I have, again, my surface. I have my low. I have my high. I've got my beam of light. And maybe I'm coming in at an oblique angle like this. Instead of having some ray coming out, I just get the entire ray reflected. Whereas with this one, I would actually also have a reflected ray. So we could call this one theta reflected, something like that. And this one right here would be the refracted. When I exceed a certain value, when I get to the point where sine of my angle is bigger than 1, there's no refracted ray. This is what's called total internal reflection. All of it got reflected. All of the ray is reflected. Okay. And so you might be wondering, okay, well, when do you get to that angle? So we come back over here. When is it all getting reflected? And the answer is if theta high exceeds what's called the critical angle, then this happens. And so I can find the critical angle using sine theta critical is NL over NH. And let's put a little box around that equation. But using the numbers that I had over here, where I had 1 and 1.45, so example for in low is 1 and in high is 1.45, what I end up getting is that the sine of the angle, so sine theta critical, would be 1 divided by 1.45. You always want the little number over the big number when taking sines. Excuse me. Then I'm basically looking at inverse sine 1 divided by 1.45, and what I get is 43.6 degrees for theta critical. So theta critical is about 43.6 degrees. Again, I got that, for those who are not so calculator savvy, by using theta critical is sine inverse, that's the sine -1 button of these two numbers. And so this is saying that for this combination of materials, if my incident angle is bigger than about 43.6 degrees, I'm not going to get light out through the other side of this interface. It's all going to be reflected. Are there any practical applications of this? Yes, there's actually quite a few. The most obvious one is fiber optics. Basically, optical fibers use total internal reflection to send signals from one end of the fiber to the other without losing very much of the signal. You do lose a little bit because there's stuff like scattering and that kind of thing. but you can send signals very long distance over optical fibers with relatively little loss compared to just taking a light outside and trying to shine it from one to another around a curved space. Okay, so that's an application of that. The other part of this video is dispersion. And dispersion actually, for what it's worth, is another effect you run into in fiber optics communications, but I'm not really going to go there right now. What is dispersion? Basically, the refractive index of your material is not actually constant. It is wavelength dependent. So we could say wavelength dependent. That means it would vary. So varies with lambda. Okay, what is the consequence of this? Well, on the one hand, it means if you're sending a broadband source, for example, white light, but also, for example, actual pulses that are used in fiber optical communications. You've heard of bandwidth before, probably. So the higher the bandwidth that you have, sort of like the higher quality, I guess you could say, the thing that you're sending is going to be. And so, but the higher the bandwidth, that also means the broader the ranges of lambdas that you're using. And if you have different wavelengths, different refractive indices for each lambda, that means that each lambda is also traveling at a different speed. In fact, the way that this tends to work is that it tends to be monotonic for optical, like for colored lights that you can see. For fiber optic communications, they actually try to pick a signal that is as near to the local dispersion minimum as possible. But either way, essentially what the effect is that colors spread out. So I'm going to put colors in quotes because this is true if you're using infrared. It's true if you're using whatever wavelengths you're operating at. Fiber optic communications, we actually use infrared, and so it's not really blue and purple and red and green. It's just different wavelengths of infrared. But the colors or different wavelengths travel different speeds, and that means they spread out. That can be in space and it can be in time as well. So spread out in space and time. For an optical pulse, or for a pulse in general traveling along a fiber optic cable, your optical signal, basically maybe you send in a pulse like this. So maybe like this is what your signal looks like going in, and then it travels along this long path, and then out the other side it may look more like this. So it's like spread out. And so, maybe this represents the word high, and on the other end you might get, it doesn't make any sense. It's garbage. It's spread out in time. And so you have to put little repeaters every so often so that when this has spread out from, say, here to, let's say, like here, you can still understand that it's, instead of being high, it's now high. It recompresses to high, and what you get out the other end is your message. Now there's another effect of dispersion, and this is the one that's usually talked about, and like your textbook talks more about this effect. It's what we usually do in introductory physics. Let's say that I send a pulse of white light across an interface like this. So I've got this white light pulse. It's coming into this interface. It has in it different wavelengths, say like violet and blue and green and yellow, all the way up through red, whatever. Well, each refractive index for those different colors is different. This angle right here, this is my incident angle. This is the same for all of them. But because we have different refractive indices, when we go to calculate the, let's say, refracted angle, remember that sine theta r refracted would be in from the incident side divided by in from the refracted side. So we'll call this in I, call this side the in R side, times sine of theta incident. Okay, and similarly, we could say therefore my refracted angle is equal to my ratio. Is equal to the inverse sine of my ratio of in I over in R times sine theta I. Now, if you're coming in from vacuum, then both in I and theta I are the same for all your different colors. But in R is different. So in R could be in R of lambda. Now, typically, it is such that in R, blue travels slower than red is kind of the normally dispersive rule. Okay, and so that means that in R is bigger for blues than it is for reds. So refractive index is a bigger number for blue than for red. That makes this number overall smaller for blue than for red, which makes the angle overall smaller for blue than for red. Okay, and so basically what ends up happening is I have blue light maybe refracting like this. I have purple light, which is even slower, maybe refracts off like this. I have green light, which refracts off maybe like this. I'm kind of exaggerating a little bit. So green light kind of coming off like this. Then I have my yellows and my oranges maybe coming out like this. And then finally, I end up with stuff that's more red. And the more red may come off like this. And so this is basically your rainbow effect that you can get with a prism. It's also why literal rainbows are formed. When you look outside on a day that it's been rainy and you see a rainbow, you can see the different colors from the rainbow. And it's because light is interacting with little water molecules that are still in the air. And it has dispersion within that water molecule. So you get this splitting of colors within the water molecule, and then those colors basically exit at different angles, and they arrive at your eye. You get all the colors arriving at your eye, but different colors are arriving from different heights in the atmosphere because of these different angles. The upshot to it is that you always have the same pattern of colors on your rainbow. When you're looking at the rainbow, it always has sort of this kind of coloring pattern, depending on what colors you see at all. You have your purples at the bottom, then you have your blues, then you got your greens, and then you've got your your yellows, your oranges, your reds. So here's the general rainbow. Now, why is it always in this order every time? Because what's basically happening is you have your water droplet. Let's say there's a water droplet here. Let's say there's a water droplet here. Let's say your eye is right over here. All right, and now I have going into the water droplet sunlight, like this. Sunlight basically all kind of at the same direction. And what essentially happens is I get my red like this, and it bounces and then comes on out to the eye. That wasn't a very good drawing of the red bouncing and coming out to the eye. Here's the red coming out to the eye. And now let's draw, say, purple. And purple kind of has a bigger angle of deflection, and thus a bigger angle of deflection down here. Or excuse me, has a bigger deflection from the mean. So it comes off here like this. And then down here, my purple, which is again doing the exact same thing as in the upper one, that one's making it to my eye, and the red one is missing my eye. And so this is lower than this one, and therefore I see the purple lower down than I see the red. And there also exists maybe a droplet here that represents blue, and one here that represents green, and so on. And that's why your rainbow colors follow that order. Now I said a moment ago they always follow that order. There's actually a interesting exception. If you see a double rainbow, that's caused by sort of an additional set of internal reflections. So you get some more total internal reflections in here and then reaching the eye. That second rainbow, the order's flipped. Red will be at the bottom, purple will be at the top. Okay, and that's dispersion. That's dispersion for you. So, and now we've kind of talked about it both in terms of time dispersion, spreading out in time as optical pulses do, and also in terms of space dispersion, spreading out like a rainbow or like from a prism side. So hopefully you enjoyed today's little video, and thanks for watching.